For decades, astronomers believed a hidden world was tugging at the outer solar system, a distant, unseen planet silently shaping the orbits of frozen objects beyond Neptune. Telescopes searched empty darkness. Calculations hinted at something massive and elusive, and the hunt became one of the greatest cosmic mysteries in science. Then, at the edge of visibility, a tiny moving dot appeared against the stars, changing everything. Pluto was not found by accident. It was discovered because something was missing, and scientists refused to stop looking. What began as a search for a powerful unknown planet ended with a strange icy world that challenged how we define planets and revealed how little we truly knew about our own cosmic neighborhood. This is the story of how the search for elusive planets finally came to an end, and why the discovery of Pluto was only the beginning. If you love the content, hit the like button and subscribe to the channel. We begin. By 1930, scientists had been searching for over 30 years for a mysterious ninth planet. Starting around 1900, careful observations of how Uranus and Neptune moved suggested something else was hiding in the darkness beyond Neptune. Another distant world was out there, far past Neptune. Finding such a faint object was like searching for a needle in an enormous haystack. Leading the search was Percival Lowell, founder of Flagstaff Observatory. Beginning in 1906, Lowell pursued the ninth planet obsessively, but he never lived to see its discovery. He never realized how close he had come to finding it himself. Unknown to Lowell, images of Planet X had been captured in 2 photographs he took roughly a year before his 1916 death. Nobody noticed the evidence. The photographic plates were filed away, and the search continued without him for another 15 years. The method was straightforward. By examining pairs of photographs taken several nights apart for any stars that appeared to have shifted position, searchers could distinguish between distant background stars and anything orbiting closer to Earth. Hundreds of image pairs were taken at Lowell Observatory and analysed using a device called a blink comparator, which helped reveal tiny differences between images. On January 29, 1930, Clyde Tombaugh finally succeeded. Comparing 2 images taken 1 week apart, Tombaugh discovered what appeared to be a moving object. Across those few days, a dim spot had moved no more than an inch. That tiny movement meant something profound, an object much closer to Earth than distant stars. Tombaugh had found Planet X, which would be named Pluto after the suggestion of 11-year-old Venetia Burney from Oxford, England, who loved classical mythology. Taken off from Cape Canaveral on an Atlas V rocket in January 2006, the New Horizons space probe began its epic journey toward Pluto. This happened just 9 years after Clyde Tombaugh's death. This tiny probe, no bigger than a grand piano, carried 30 grams of Tombaugh's ashes as tribute to the discoverer. For mission leader Alan Stern, this fulfilled a promise made to Tombaugh. While seeking funding for the mission, Clyde died in January 1997. Before that, he had asked if his ashes could be sent on the journey if a mission ever launched. When New Horizons was ready in summer 2005, Stern contacted the family. They made it happen, creating a human connection between the discoverer and the explorers. Leaving Earth at 1626 kilometers per second, New Horizons was the fastest probe ever launched from our planet. Reaching Jupiter in just over a year, it got a gravity boost from the gas giant. This sent it hurtling across space with all non-essential systems shut down to save energy. The probe slept through most of its 8-year voyage in darkness. After 20 years of planning and dreaming, the team could only wait and hope as it made its way toward the last unexplored world in our solar system. While the voyage proceeded smoothly, Back on Earth, the mission's status was about to take an unexpected turn. Starting with the 1992 discovery of Albion, Pluto's description as a planet orbiting alone in the farthest reaches came under scrutiny. Pluto wasn't so lonely after all. This region was filled with orbiting objects. As we explored the Kuiper Belt, we discovered they were far from just fragments. This was a region filled with Pluto-like worlds. Quaoar, half Pluto's size, was discovered in June 2002. Sedna, a large minor planet on an 11,400-year orbit, was found in November 2003. Haumea, with 2 tiny moons, was discovered in December 2004. Makemake, perhaps 2/3 Pluto's size, was found in 2005. Then Eris, almost Pluto's size if not bigger, was spotted in January 2005. These discoveries forced the International Astronomical Union to reconsider what makes a planet. In October 2006, they published 3 requirements for planethood. 1. It must orbit the Sun. 2. It must be massive enough to form a sphere under its own gravity. 3. It must be massive enough to clear its orbit of other objects. Pluto passes the first 2 tests. It orbits the Sun every 248 years and is nearly perfectly spherical. But regarding the 3rd requirement, Pluto isn't massive enough to blow away all the dust and debris in its orbit. It fails to make the cut. Since September 2006, Pluto has been officially designated a dwarf planet, a sphere orbiting the Sun, yes, but not a planet. The 3rd criterion separates the chosen 8, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune from the rest. Because if Pluto was a planet, so would be Sedna, Eris, Makemake, and dozens or hundreds of other Kuiper Belt objects. By the time New Horizons entered its final approach, it had changed from a planetary exploration mission to the first ever mission to a dwarf planet. After nearly 10 years in icy darkness, New Horizons awoke from hibernation. In July 2015, it began beaming back images from its close encounter. These revealed Pluto not as a frigid, featureless rock, but something far more captivating. Planet or not, Pluto was beautiful. The images showed complexity across its freezing -230 degrees Celsius surface. It had all the features of a dynamic, active world. The blemishes we gazed at from distance were no longer just smudges, but high-definition images revealing an extraordinary range of geological forms. New Horizons first spotted Pluto shortly after launch as just a dot. Year by year, that dot grew brighter. Even after 9 years of flight, it was only 2 pixels across just 10 weeks before arrival. Then the images got better and better. Suddenly, as they flew past, it transformed from a blurry view to a phenomenally complex world. There were mountain ranges, gorges, and glaciers. An atmosphere glowed up to 500,000 feet high. There were polar caps, evidence for a liquid ocean inside, 5 spectacular moons, and much more. It was almost overwhelming to see what an amazing place Pluto was. Alan Stern said the solar system had saved the best for last. This landscape was built from frozen nitrogen, with soaring mountains and complex ridged terrain. But one feature leapt from the images more than any other. Running across the equatorial region, we could see a giant heart-shaped plain of frozen nitrogen, methane, and carbon monoxide stretching 1 million square kilometers. Named Tombor Regio, or Pluto's heart, this region captivated scientists. The western lobe, called Sputnik Planitia, has at its eastern edge mountains of pure frozen water ice rising miles above the frozen plain. But it wasn't just the mountains and romantic shape that caught attention. There was something strange about Sputnik Planitia that set it apart. Everywhere across Pluto's surface, we saw craters, impact scars accumulated over billions of years, just like on our moon. except on Sputnik Planitia. This icy plain appeared unblemished, utterly smooth for miles without a single crater. Looking closer at this region, it appeared stranger still. Detailed imagery showed puzzling patterns, hexagons and pentagons crisscrossing the frozen nitrogen exterior. This suggested something intriguing happening beneath. New horizons provided a hint that Pluto's heart was beating. The geometric patterns on Sputnik Planitia may be distant, but they're remarkably familiar. We see these patterns throughout nature, from the sun's surface to boiling water. They're characteristic patterns of convection, forms we see when a heat source causes material to rise, cool, and fall back down. Underneath this region of Pluto, there appears to be a heat source creating circulating convection currents. These melt the nitrogen ice, causing it to rise, cool, and fall again. This constantly resurfaces the area, removing impact scars and leaving characteristic convection cells behind. We don't know for certain where this heat comes from, but many scientists believe that below the glacier's surface there was once, and may still be, a liquid water ocean. This ocean could explain the strange patterns. Only a small temperature difference between the underground ocean and frozen nitrogen above is needed to create the convection currents producing the crater-free plain we see today. Just imagine, billions of miles from the Sun, on the frozen frontier of the outer solar system, there may still be a water ocean. As New Horizons left Pluto behind, NASA turned its camera back toward the dwarf planet. This revealed a hazy nitrogen atmosphere, a blue sky above a possible water ocean, 4.8 billion kilometers from Earth. Today, New Horizons continues outward into the furthest reaches. In January 2019, 3.5 years after leaving Pluto, it revealed another world, the first image of Ultima Thule, the snowman-shaped dwarf planet. By visiting these outer worlds, we've illuminated the darkness, explored places beyond imagination, and opened an unfinished chapter in our solar system's story. To Romans, Jupiter was king of the gods, ruler of the heavens, and a figure of power with a thunderbolt in one hand and an eagle by his side. The name Jupiter means sky father, constructed from Latin words dies, day or sky, and pater, father. As often happens with mythology, truth lurks among legend. In size alone, Jupiter is by far the biggest planet in our solar system. Its mass is a staggering 1,900 trillion kilograms, 2.5 times bigger than all other planets combined. It's so big that if alien species observed our system from a distant galaxy, the Sun and Jupiter might be all they could see. With a diameter of 152,284 kilometers at the Jovian equator, Earth would fit inside Jupiter over 1,300 times. Yet this giant is made almost entirely of gas, 89% hydrogen and 10% helium. It's far less condensed than any rocky planet, with density far smaller than Earth's. 1,326 grams per cubic centimetre compared with Earth's 5,513. Despite its size, Jupiter has the shortest day of any planet, completing one rotation every 9 hours, 55 minutes and 30 seconds. It whips around on its axis at 45,000 kilometers per hour. In the last 50 years, our knowledge of Jupiter has grown exponentially. We've gained deeper understanding of its role in shaping the solar system. No longer just the beautiful banded world we see through telescopes, this is a planet we've explored up close. Pioneer 10 provided our first close glimpse in 1973, becoming the first planetary explorer to cross the asteroid belt boundary. From just over 130,000 kilometers away, it took close-up images, sending back over 500 precious pictures before flying to the solar system's edges. Just over a year later, Pioneer 11 followed, sweeping within 43,000 kilometers of Jupiter's cloud tops before heading towards Saturn. Voyagers 1 and 2 passed Jupiter in the late 1970s, taking extraordinary images of both planet and moons as part of their grand tour. This was historic. We had hints, but it wasn't until Voyager went close and took amazing pictures of the moons that we really began understanding how complex the worlds around Jupiter are and what variety exists. The Galileo spacecraft became our first long-term Jovian resident, entering orbit on December 7, 1995. Galileo spent 2 years touring Jupiter, exploring as never before. It released a probe that parachuted through 150 kilometers of Jupiter's atmosphere, collecting data for almost an hour before being destroyed by intense pressure and temperature. Galileo was also the first mission to explore Jupiter's extraordinary moons in detail. It helped us see that Jupiter lies at the center of an extraordinary system with more natural satellites than any other planet. 79 moons at the time of writing. 12 were discovered since early 2017, and the number will likely rise as we explore in greater detail. Most of Jupiter's moons, 63 of them, are little more than rock fragments, none bigger than 10 kilometers in diameter. They're captured asteroids now orbiting the planet rather than the Sun. But Jupiter has 4 giant moons. Fiery Io is the most volcanically active world in the solar system, its surface littered with lava lakes. Icy Europa is at the other extreme, with frozen surface protecting a global water ocean beneath. Marble-like Ganymede is Jupiter's largest satellite and the only moon with its own magnetic field. Callisto, the outermost Galilean moon, is also thought to have a subsurface ocean. Each moon has unique, intriguing character, all visible from Earth using just binoculars. In August 2011, NASA launched its latest Jupiter mission, Juno. After travelling 5 years, it reached Jupiter in July 2016, entering a perilous elliptical orbit, taking it from 8 million to just 4,000 kilometres above Jupiter's clouds. Juno is designed to probe Jupiter's origin and evolution by measuring the planet's composition and its magnetic and gravitational fields. This allows building a detailed picture of the interior. It also has the best camera ever pointed at Jupiter, sending back incredible images since 2016. What JunoCam's images show us is that Jupiter is like visiting an impressionist art gallery. We're seeing Jupiter and atmospheric features up close with the highest resolution ever achieved. We're seeing the zones, belts, and jet streams of Jupiter in more detail than ever before. For all the majesty these probes have brought us, Jupiter remains vast and distant, sitting on average 588 million kilometers from Earth. It's easy to think of this world as benign beauty, a jewel to marvel at. But what makes Jupiter the true king of heavens is not just beauty, but its influence over the solar system's unfolding story. As we've explored this world ever closer, we're discovering that Jupiter's effect on entire planets' fates is far more direct and violent than we ever imagined. Its massive gravitational field exerts control not just over its moons, but over every asteroid, world, and life force in the solar system whose destinies it still holds. To understand Jupiter's awesome power, we don't need a billion-dollar spacecraft, rocket, or even telescope. We need only look at the ground beneath our feet. Our planet's surface is littered with evidence of our distant godfathers' meddling. Written across our planet in violent gravitational handiwork are, at the most recent count, 190 visible impact craters. This doesn't include thousands more that disappeared as Earth's active geology continually renewed itself. One famous example is Meteor Crater, also known as Barringer Crater, in northern Arizona desert. It measures over 1,000 meters across and, at its deepest point, drops 100 meters below the crater rim. In the late 1800s, geologists believed this vast feature was created by the San Francisco volcanic field lying just miles to the west. But in 1903, Daniel Barringer, a mining entrepreneur and Theodore Roosevelt's hunting friend, began extensive investigation. He published findings suggesting it wasn't created by a volcano, but by a large incoming projectile from outer space. This was the first time anyone suggested such a theory. Barringer backed it up with geological evidence, including discovering around 30 tons of large iron oxide fragments from the suspect meteorite. At the time, there was much skepticism that an incoming meteor could create such massive geological feature. But ignoring overwhelming scientific consensus, Barringer put his money and reputation where his mouth was. He formed Standard Iron Company with the sole aim of mining the crater for the 100 million tons of iron ore he believed lay underground. Even at 1903 prices, if correct, that iron ore would have been worth over $1 billion. Unsurprisingly, he continued digging to depths over 400 meters pursuing the meteoric remains. Unfortunately, it would take 27 years of mining to discover what we know today. The meteorite that impacted in that Arizona desert was much smaller than predicted. Current measurements suggest around 300,000 tons, 300 times less than he thought. With advanced studies in such impacts, most of the nickel-iron meteorite was vaporized as it struck ground at around 43,000 kilometers per hour. Barringer's money evaporated, though not as quickly as the meteorite. By 1929, operations stopped and most of his fortune was gone. It would be 50 years before Barringer's work was fully verified. A landmark 1963 publication analysed similarities between the Barringer site geology and craters created from testing nuclear weapons in Nevada. The study showed that the shocked quartz identified at Barringer crater could only have formed at the enormously high pressures and temperatures created by nuclear explosion, or by the extraordinary impact dynamics of a 300,000-ton meteorite crashing into ground. We know now that the giant rock creating the crater, like most meteorites striking Earth, was once an asteroid, just one of millions of rocks circling the Sun between Mars and Jupiter's orbits. Most have been in stable orbit for billions of years, rocky leftovers from the solar system's birth. They orbit in an eternal junkyard of planetary cast-offs. But occasionally, one of these huge rocks is propelled toward the inner solar system. More often than not, we think the nudge causing it comes from Jupiter. Why this happens and how Jupiter exerts its power not just over the asteroid belt, but over all worlds around our Sun, is a story we're only beginning to understand. From our home here on Earth, it's hard to imagine the vast reaches of space extending beyond our little bubble and the huge expanse of time over which cosmic events play out. But all evidence suggests that around 4.5 billion years ago, Jupiter's orbit began changing. As it did, it triggered unprecedented violence during which the young solar system was utterly transformed. We know this because the marauding planet left a trail of destruction in its wake that we've only just begun to explore. As we've attempted to uncover the 5 billion year history of our solar system, we've repeatedly looked to the 8 planets and their orbiting moons to provide clues filling gaps in our story. In the last 50 years, dozens of missions have crossed our thin blue line on the way to those worlds. But only once have we sent a spacecraft to explore a very different type of world, to search among the rubble of our solar system's earliest days and explore the handful of worlds that never quite made it. Sometimes the answers lie in the gaps. Launched on September 27, 2007, the Dawn space probe took off from Cape Canaveral on a mission to explore the 2 largest asteroid belt objects, Vesta and the dwarf planet Ceres. This $450 million project was part of NASA's low-cost discovery program, one of a series of missions designed to be faster and cheaper to deliver. But this was no bare-bones mission. Equipped with the most advanced ion propulsion system ever used in outer space, Dawn would reach the asteroid belt and become the first craft in human exploration history to enter orbit around Ceres. Yet without a major planet in its itinerary, world attention only seemed to glance toward this mission. For the most part, its extraordinary findings slipped between gaps of public attention. The Dawn mission's aim was straightforward. This would be the first spacecraft to travel to the asteroid belt, the first to orbit an object in this uncharted region, and the first to visit a dwarf planet. This mission profile was designed to allow scientists a rare chance to travel deep into the past and glimpse the earliest moments in our solar system's origin. The mission let us explore the evolution of Vesta and Ceres, two very different objects frozen in time for billions of years since they faltered and failed in the process of becoming fully fledged planets. Travelling to the asteroid belt would be a slow but steady voyage for Dawn. After hitching a conventional ride into space on the Delta II rocket, the spaceship began firing thrusters to orient and propel itself away from Earth toward Mars. Dawn's ion thrusters were an efficient but gentle propulsion form, taking 4 days at full throttle to accelerate from 0 to 96 kilometers per hour. It's not exactly a sports car. But for efficiency, the ion propulsion system is difficult to beat. Powered by a 10 kilowatt solar array, Dawn's engines ran for almost 6 years across the 11-year mission lifetime. It propelled the craft across space using less than 400 kilograms of xenon fuel while reaching speeds of 41,360 kilometers per hour. Its trajectory took it on a 16-month journey to Mars, where a gravitational kick sent it toward the asteroid belt and onward to Vesta, its first destination. Almost 500 million kilometers from the Sun, the asteroid belt lies halfway between Mars and Jupiter. It's the boundary line between the 4 rocky worlds orbiting closest to the Sun and the giant gas and ice planets lying beyond. Made up of millions of rock pieces from the solar system's dawn, it's a graveyard of failed planets, remnants from the heyday of planetary construction. We often imagine the asteroid belt as a dense, unnavigable mass of tumbling rock. In reality, it's quite different. The total mass of all those rocks is estimated at 3 × 10 to the 21st power kilograms. Although that's an enormous number, it's just 4% of our Moon's mass. A third of that mass is found just in the largest object, Ceres. The rest of this cosmic junkyard comprises objects covering a vast range of sizes. On one end, we think there are at least a couple hundred asteroids larger than 100 kilometers. Then come a million or so stretching to at least 1 kilometer or more. There's a countless spread of smaller objects numbering in the millions and billions, depending on how small you want to go. All this sounds like it should make for a crowded environment full of collisions. But even with that many objects, the space they occupy is so unimaginably vast, spread across 13 trillion cubic miles, that the average distance between any 2 large asteroids is approximately 2 million miles. That's 8 times the Earth to Moon distance. These distances are so large that when we send spacecraft to the outer solar system, the chances of hitting anything are so small that engineers don't need to make any course corrections to pass through. In fact, if you were standing on an asteroid, you'd be lucky to see another one. If you did, it would appear as little more than a tiny point of light in the darkness. As it travelled through this vast emptiness in early summer 2011, the Dawn spacecraft slowly began bringing its first target into view. From over 1.2 million kilometers distance, Dawn took its first photograph of Vesta against the backdrop of 1,000 stars. Over the next 2 months, Dawn homed in on Vesta, chasing it across vast reaches of space. On July 16, 2011, Dawn became the first spacecraft to enter within the gravitational hold of an asteroid belt object. For the next 14 months, it would explore this extraordinary ancient object, providing a glimpse of our solar system in its very earliest days. When German astronomer Heinrich Olbers first discovered Vesta in 1807, it was the fourth asteroid discovered after Ceres, Pallas and Juno, hence the 4 in its formal designation. Olbers was convinced he had found remains of a lost planet destroyed in some long-ago collision. Just like the other 3 objects, Vesta was at first given full planetary status. This brought the number of classified planets in the solar system at that time to 11. It wasn't until 1845, nearly 40 years later, that a flood of further discoveries began. This quickly increased the number of objects in this region to a point where it was clear they couldn't be classified as planets. So in the 1850s, 15 planets became 8, and the classification of these objects as a different class of minor planet, asteroids, had begun. 160 years later, as Dawn began its year-long residency near Vesta, it soon became apparent that Olbers' suggestion that this was a fragment of a long-lost planet wasn't so far off. Vesta is a spheroid-shaped rock, 530 kilometers in diameter and pockmarked with impact craters. The most striking example is the crater Rhea Silvia, which at 500 kilometers wide and 20 kilometers deep is one of the largest impact craters in the solar system. At its center is a mountain rising into the blackness 22 kilometers from the crater floor. This makes it the second tallest peak in the solar system after Mars's Olympus Mons. What's particularly extraordinary about this crater is that we've long suspected that a particular class of meteorite found on Earth, known as H-Ed meteorites, actually comes from material blown off Vesta's surface when this impact occurred around 1 billion years ago. Using Dawn's instrumentation, we were able to directly measure the geology of rocks in Rhea Silvia. When compared with Earth samples, we concluded they are of the same origin. In one of the most beautiful examples of geological analysis in the subject's history, we now know we can hold a piece of this faraway asteroid in our hands and directly analyze the secrets hidden within it. When taken together, the HED meteorites and Dawn spacecraft findings have enabled us to paint a detailed picture not just of Vesta today, but also of its history. Dawn revealed that Vesta has a metal-rich core, just like all terrestrial planets, including Mercury, Mars, Venus, and Earth. Analysis of its surface geology enabled us to date the asteroid's formation to a couple million years after the first solid objects began taking shape in the solar system. These are just 2 clues pointing to an extraordinary conclusion. Vesta is perhaps the last remaining example of a protoplanet, a half-formed world from the very earliest solar system days, frozen in time. This is a stage every world we know passed through, including Earth. Vesta was on the way to becoming a planet almost 4.5 billion years ago, but something happened to stop its progress. While other worlds went on to flourish, and other protoplanets disintegrated in violent early solar system collisions, Vesta somehow survived. It's a fossil of planetary formation for us to not only look at, but through a quirk of fate, actually hold. But this wasn't the end of Dawn's dive into our deep history. Departing Vesta after 14 months of study, Dawn fired its ion drive, leaving orbit and heading off for its second planetoid rendezvous at the largest asteroid, Ceres. Dawn arrived at dwarf planet Ceres in early March 2015. From the very first moments of observations, it sent back astonishing images. Very little was known about Ceres before our spaceship arrived, but it soon became clear this was a rock with far more story to tell than we ever imagined. It's a story that would help reveal a new perspective on the deep history of our solar system and the enormous influence Jupiter has exerted over it. Italian astronomer Giuseppe Piazzi discovered Ceres on January 1st, 1801. At first, he reported his findings as the discovery of a new comet in the region of space between Mars and Jupiter. But it seems from the start that all his instincts told him this was something else. In announcing his observations in a letter to two fellow astronomers, he noted that since its movement is so slow and rather uniform, it had occurred to him several times that it might be something better than a comet. Piazzi and his colleagues speculated that, rather than a comet, they might have found something even more spectacular, a new planet. But after just 41 days of observation, Piazzi fell ill. The path of the newly discovered object strayed into the direct glare of the sun. In a twist of high astronomical drama, the newly found planet Ceres was lost. With just a tiny number of observations across a small piece of sky, calculating Ceres' orbit was deemed impossible using the mathematics of the time. Many contemporary great mathematical minds predicted it might never be found again. It would take the work of a young German mathematician, Friedrich Gauss, to solve the problem. Attracted to the difficulty and elegance of using mathematics to compute the orbit from just a few coordinates, Gauss pioneered a novel mathematical method. This allowed him to calculate Ceres' path using just 3 of Piazzi's original observations. On the very last day of 1801, 2 astronomers using Gauss's methods searched the region of sky to which the calculations guided them. To everyone's delight and relief, they recovered Ceres from the darkness. Gauss became a mathematical superstar, and Ceres, firmly back in our sights, was stamped with the classification of a planet. For the next 50 years, Ceres and its companions, Vesta, Pallas, and Juno, remained listed as planets. But as we've seen, the discovery of a raft of other objects in this space region gave rise to our identification of the asteroid belt. For Ceres, it was downhill from there. In 2006, it was classified as a dwarf planet. For the next 160 years, little was known about this tiny planet orbiting the Sun at a distance of 413 million kilometers. We knew it was the biggest asteroid belt object, and the only object among millions of asteroids that was large enough to have been rounded by its own gravity. We could make a good approximation of its size at around 1,000 kilometers in diameter and composition of rock and ice. But when it came to surface features, even powerful Hubble Space Telescope could make out only the vaguest of features. Intriguingly strewn across its surface, it would take Dawn's arrival for us to truly understand the complexity of this world and its history. Even in the early approach phase of the mission, Dawn was able to capture imagery quality that at once gave new perspective on the long-hidden surface. It was no surprise to find it heavily cratered, but while speeding towards Ceres, Dawn beamed back a series of mysterious images revealing a number of bright spots on the surface of what we thought would be a dull, dead, frozen world. Not what you'd expect on a planet assumed to be entirely geologically inactive. The brightest of all these highly reflective areas was imaged near a massive crater known as Ockhiter. At 92 kilometers wide and 2 kilometers deep, it's one of the biggest on Ceres' surface. Spot 5, as it became known, is in the crater's center and became the focus of intense investigation as Dawn began its 3.5-year residency in orbit around Ceres. The crater is thought to have formed from a large-scale impact around 80 million years ago. So the presence of what appeared to be geologically active material on the surface was particularly surprising and at first left mission scientists perplexed. Not only that, but a haze was also seen to periodically appear above Spot 5, suggesting something was going on beneath the surface. After detailed analysis using Dawn's full range of imaging and spectroscopic capabilities, we now believe Spot 5 is the result of a geological hotspot. The brightness is created by the highest concentration of carbonate minerals ever found outside Earth in a dome structure right in the crater's center. Why does this matter? We know this type of salt can only be formed in the presence of liquid water. It's almost certain that an impacting asteroid could not have delivered such material to Ceres' surface. So the upwelling in which it's found suggests it comes from deep within this world. It now seems Spot 5 is the remains of an ice volcano, one that is perhaps still partially active and thus able to create the haze we've observed. The two brightly coloured patches inside it are thought to be the salty residue left by this ancient formation, deposits of sodium carbonate from an erupting ice volcano that may have first been triggered by the impact creating the crater. However, the dome-like shape upon which the deposits sit is almost certainly evidence of geological activity below the surface, suggesting hydrothermal activity was involved in bringing the salts to the surface. Spot 5 is far from isolated. We've now seen areas like the ones in Okator all over Ceres' surface. This begins to paint a tantalizing picture of Ceres' past, a past where heat from within the planet created a subsurface ocean, or at least localized pockets of water that surged upwards in the form of great ice volcanoes, bringing with them the carbonate salts we see sparkling today on the asteroid. As dawn delved deeper, beneath the surface, the surprises kept coming thick and fast. Dawn was able to accurately measure the overall density of Ceres and found it to be 2.16 grams per cubic centimetre. This is less than you'd expect for a rocky body. Ceres is about 2/3 the density of our Moon, which suggests that as well as rock, the asteroid must also hold significant amounts of water ice. This had been suspected long before Dawn arrived, but with our eyes and ears now at work as Dawn circled Ceres, it was able to take precise measurements and uncover anomalies in its orbit that revealed something remarkable about this lump of rock and ice. By carefully mapping the shape and gravitational field, we found that the rock and ice weren't evenly distributed. It appears that Ceres' interior is nothing like that of other asteroids in the belt. Instead, it appears to have a rocky core surrounded by an icier crust. This is not the jumbled structure of an asteroid. The differentiation into layers discovered by Dawn is something we only see in planets. It seems that around 4.5 billion years ago, Ceres had taken its first steps to becoming a fully fledged world. And then something went catastrophically wrong. We now think that 4.57 billion years ago, a young rocky planet began forming in the region we call the asteroid belt. In its infancy, this protoplanet was a water world, warmed from within by heat left over from the violence of its birth. Even in this frozen region of space, orbiting 413 million kilometers away from the weak young sun, a deep saltwater ocean encircled young Ceres. It was protected from freezing space temperatures beneath a thin layer of ice. Across this ancient embryonic world, ice volcanoes broke through, transforming and renewing the surface as it was bombarded by the bodies swarming around it. Today, we see just the lifeless remains of this geologically active world in the distinct mountainous landscape and sparkling salts that clothe it. But the subsurface ocean is long gone, locked away as a thick ice layer between the surface and core. This is a nascent planet that has been in deep stasis for billions of years, frozen in time. It is a precious piece of history, an artifact allowing us to glimpse our origins and understand just how precarious a time this was for every planet, including our own. We now think that before Ceres could fulfill her potential, a great disturbance sent shockwaves through what would eventually become the asteroid belt and cut its young life short. The vast amounts of rock and ice making this part of the young solar system such a rich breeding ground for planet birth were wiped clean of almost all building material. This left just a fraction of the material needed to build a planet and nothing from which Ceres could grow. Computer simulations suggest that originally the asteroid belt contained enough material to build an Earth-sized planet. Perhaps that was once Ceres' destiny. Perhaps it was even destined to become a subterranean water world capable of supporting and nurturing life. But before any carbon chemistry could spark into seeds of life, Ceres' fate was sealed. Robbed by the wanderings of a giant lying beyond in the darkness, we now suspect that at this early time in the solar system's life, as Jupiter circled the young Sun, something caused the giant planet to change course and spiral inwards toward the Sun. It ploughed right through the asteroid belt. The resulting gravitational chaos scattered the asteroid belt's contents far and wide. Embryonic planets were knocked out from their orbits. The building material of these planetesimals was thrown out and inward toward the Sun. Jupiter's charge displaced 99.9% of the material in this space region. Ceres was left half-formed, half-built, but with nothing more from which to grow. In this part of the solar system, at least, the planetary construction business was shut down for good. How do we know such a dramatic turn in the solar system's history took place? The greatest evidence has come not from our own system, but from studying other star systems and their planets, a science field that has exploded in the last 30 years. Until the 20th century, the only evidence of how planetary systems formed and functioned came from one single source: Earth's solar system. Our own backyard was the one place we had technology to study. That meant our view of how planetary structure worked was deeply skewed toward the seemingly simple structure of a star at the center, 4 small rocky planets orbiting it, then a ring of millions of rocky pieces, remnants from its formation, followed by a series of 4 more planets, the gas giants. It has a pleasing regular structure about it. All the rocky planets sit close to the star, and the gas giants orbit further out. We suppose this must be the natural order of things, the way solar systems have to form. But that all changed when technology arrived, allowing us to detect planets around distant stars. It soon became clear that our solar system is not typical at all. It may in fact be very odd indeed. In most planetary systems we've observed, the setup is remarkably different from our own. As we've extended our gaze and explored the structure around other stars with exoplanet hunting technology like the extraordinary Kepler telescope, we've begun seeing that one of the most common categories of planet is completely missing from our own system. Inward of Mercury, our solar system is essentially an empty void. But look at the equivalent region around most stars we've studied, and we often find it packed with a completely different planet class: super-Earths. These worlds are between 2 and 8 times Earth's mass with thick hydrogen-rich atmospheres. They sit incredibly close to their stars, orbiting at a rate that makes the head spin. The first discovery of a super-Earth around a main sequence star like our own was made back in 2005 by a team led by Eugenio Rivera. Using data from the Keck Observatory in Hawaii, they found Gliese 876d, an exoplanet almost 7 times Earth's size, orbiting just 3 million kilometers away from its red dwarf star Gliese 876, thought to be a rocky planet with surface temperatures estimated to approach 341 degrees Celsius. With an orbital period of just under 2 days, this is a world completely inhospitable to life. To understand why this rocky planet is found so close to the Sun, we need to understand the rest of the planetary system. In the case of Gliese 876, that means looking at the 3 other planets circling further out from the star. The first of these planets to be discovered, and one of the earliest exoplanets ever found, was Gliese 876b, discovered in 1998 by a team led by Geoffrey Marcy. This was a gas giant world 2 times Jupiter's mass, but unlike Jupiter, which orbits around 70 to 78 million kilometers from the Sun, Gliese 876b orbits at just 3.3 million kilometers from its parent star. This is far closer than even Mercury orbits our Sun at 58 million kilometers. This discovery was completely unexpected and at first didn't make sense. How could a gas giant form so close to its star where temperatures should be far too high for gases to condense? The answer is that it couldn't have formed there. Gas giants like Jupiter require enormous amounts of hydrogen and helium gases to reach their massive size. But close to a young star, the intense radiation blows these light elements away before they can accumulate into planet-sized bodies. Gas giants can only form in the outer, colder regions of a solar system where temperatures are low enough for gases to condense and accumulate. The only possible explanation was that Gliese 876b had formed much further out in the system, where conditions were suitable for a gas giant to coalesce and then migrated inward over time. This wasn't just wild speculation. As astronomers began detecting more and more exoplanets throughout the late 1990s and early 2000s, they discovered that gas giants orbiting very close to their stars, now called hot Jupiters, were remarkably common across the galaxy. This fundamentally changed our understanding of how planetary systems form and evolve. Planets don't necessarily stay where they form. They can move, sometimes dramatically, through their solar systems, and when they do, they reshape everything around them. As a migrating gas giant ploughs through its solar system, it encounters smaller rocky planets that formed in the inner regions. These rocky worlds face a stark choice: be swept up and consumed by the gas giant, be flung out of the system entirely into interstellar space, or be pushed inward into even tighter orbits around the star. This third option explains the super-Earths we see huddled close to so many stars. They're rocky planets that survived their system's upheaval by moving closer to their sun, finding refuge in the scorching inner zones where they now reside. The discovery of hot Jupiters transformed planetary science. These gas giants, often larger than Jupiter, orbit their stars in just days or even hours. Some orbit so close that their atmospheres are being stripped away by stellar radiation. Others are tidally locked, with one side permanently facing their star in eternal daylight, while the other freezes in endless night. The first hot Jupiter discovered was 51 Pegasi b, found in 1995 by Michel Mayor and Didier Queloz, a discovery that would eventually earn them the Nobel Prize in Physics. This gas giant, about half Jupiter's mass, orbits its sun-like star every 4.2 days at a distance of just 8 million kilometers. The discovery shocked the astronomical community because it contradicted everything we thought we knew about where gas giants should exist. Since then, we've discovered thousands of hot Jupiters. Each discovery reinforces the same conclusion: planetary migration is not rare or unusual. It appears to be common, perhaps even the norm, in planetary system evolution. If migration is happening in systems across the galaxy, then our own solar system almost certainly experienced it too. This brings us back to Jupiter and what planetary scientists now call the Grand Tack hypothesis. Computer simulations run over the past decade suggest that shortly after Jupiter formed, around 4.5 billion years ago, it began spiraling inward toward the Sun. As it migrated, Jupiter's immense gravity, 2.5 times the mass of all other planets combined, acted like a cosmic bulldozer. As Jupiter moved through the region that would become the asteroid belt, it scattered the material there. Rocky building blocks that had been accumulating to form planets were flung in all directions. Some were thrown outward into the outer solar system. Others were sent plunging into the Sun. Still others crashed into the forming inner planets, including Earth. Jupiter displaced approximately 99.9% of the mass that had existed in the asteroid belt region. This explains one of the solar system's great mysteries. Why is the asteroid belt so empty? Today, the total mass of all asteroids combined is just 4% of our Moon's mass. Yet that vast region between Mars and Jupiter should have contained enough material to build an Earth-sized planet. Computer models of solar system formation consistently predict a planet should have formed there. But it never did, because Jupiter's migration scattered almost all the building material before a planet could coalesce. Jupiter's migration also explains another puzzle. Why is Mars so small? Mars has just 11% of Earth's mass. It's smaller than Venus, and Earth, despite being further from the Sun, where more building material should have been available. But Mars sits right at the edge of the asteroid belt, exactly where Jupiter's inward migration would have depleted the most material. Mars never had enough material to grow large because Jupiter stole it away. But Jupiter's migration didn't end in the inner solar system. Here's where the story takes a remarkable turn. Shortly after Jupiter began its inward journey, Saturn finished forming and also began migrating inward, following Jupiter's path. When Saturn caught up to a certain distance from Jupiter, something extraordinary happened. The two giant planets became locked in what astronomers call orbital resonance. This occurs when two orbiting bodies exert regular, periodic gravitational influence on each other because their orbital periods form a simple numerical ratio. In Jupiter and Saturn's case, they likely entered a 2.3 resonance, meaning Jupiter completed 2 orbits for every 3 Saturn orbits. This resonance dramatically amplified the gravitational interaction between the two planets. Their combined gravitational influence on the disk of gas and debris surrounding the young Sun created a powerful feedback effect. Instead of continuing to spiral inward toward the Sun, the two planets began moving outward, back toward the outer solar system. This dramatic reversal, Jupiter migrating inward, then tacking back outward like a sailboat changing direction, is what gives the grand tack hypothesis its name. As Jupiter and Saturn migrated back outward, they continued reshaping the solar system. They likely encountered the ice giants Uranus and Neptune, gravitationally scattering them into even more distant orbits. The grand tack connects to another major theory about solar system evolution, the Nice model, named after the French city where it was developed. This model describes how the outer planets' orbits changed dramatically about 600 million years after the solar system formed, around 4 billion years ago. According to the Nice model, the 4 giant planets originally orbited much closer together than they do today. But as they interacted with the disk of debris beyond Neptune, what would become the Kuiper belt, their orbits slowly changed. Eventually, Jupiter and Saturn crossed through another orbital resonance, triggering a period of instability. During this upheaval, the orbits of all 4 giant planets changed rapidly. Uranus and Neptune were scattered outward. As they ploughed through the Kuiper belt, they sent countless icy bodies careening through the solar system. Many were ejected entirely. Others plunged inward, bombarding the inner planets in what's called the Late Heavy Bombardment. Evidence for this bombardment is written on the Moon's face. The large dark patches we see, the Luna Maria, are ancient lava flows that filled enormous impact basins created during this violent period. Earth was struck even harder than the Moon, though our active geology has erased most of the evidence. Interestingly, this bombardment may have been crucial for life on Earth. Many of the impacting objects were comets and asteroids from the outer solar system, rich in water and organic molecules. Some scientists believe these impacts delivered much of Earth's water and the chemical building blocks necessary for life. So Jupiter's influence on Earth has been profound and paradoxical. On one hand, Jupiter's early migration disrupted the inner solar system, scattering asteroids that still occasionally threaten Earth today. On the other hand, that same migration may have delivered the water and organic materials that made Earth habitable. Jupiter's gravity also continues to protect Earth today. Its immense gravitational field acts as a shield, deflecting or capturing many comets from the outer solar system that would otherwise pass through the inner solar system. Some calculations suggest that without Jupiter, Earth would be struck by devastating comets and asteroids far more frequently, perhaps too frequently for complex life to have evolved. However, this protective role can be overstated. Jupiter's gravity also perturbs objects in the asteroid belt and Kuiper belt, occasionally sending them inward toward Earth. So Jupiter both protects and threatens us. But on balance, most scientists believe Jupiter's presence has been beneficial for Earth and for the development of life. While Jupiter commanded the inner solar system during the Grand Tack, Saturn played an equally important role. Saturn is the solar system's second largest planet, with a mass 95 times Earth's. Like Jupiter, it's a gas giant composed primarily of hydrogen and helium. But Saturn is far less dense than Jupiter. In fact, Saturn is the least dense planet in the solar system. If you could find an ocean large enough, Saturn would float. Saturn is perhaps the most beautiful object in the solar system, crowned by its magnificent ring system. These rings stretch over 280,000 kilometers from the planet, but are remarkably thin, in some places just 10 meters thick. From a distance, they appear solid, but they're actually composed of countless individual particles, ranging from tiny grains to chunks as large as houses, all orbiting Saturn independently. When Galileo first observed Saturn through his telescope in 1610, he was puzzled by what he saw. His telescope wasn't powerful enough to resolve the rings clearly. He described Saturn as having ears or handles on either side. 2 years later, when Earth's viewing angle changed, the rings appeared edge-on and seemed to disappear entirely. Galileo was baffled, writing that Saturn had swallowed his children, a reference to the Roman myth. It wasn't until 1655 that Dutch astronomer Christian Huygens, using a more powerful telescope, correctly identified the appendages as a ring system. He proposed that Saturn was surrounded by a thin, flat ring that nowhere touched the planet. Over the following decades, astronomers discovered the rings were divided into multiple bands separated by gaps. For centuries, astronomers could only observe Saturn and its rings from Earth, seeing limited detail. That changed on October 15, 1997, when NASA, the European Space Agency, and the Italian Space Agency launched the Cassini-Huygens spacecraft on a mission to explore Saturn up close. The journey took 7 years. Cassini used gravity assists from Venus twice, then Earth, and finally Jupiter to reach Saturn. On July 1, 2004, Cassini fired its main engine for 96 minutes, slowing enough to be captured by Saturn's gravity. It entered orbit around the ringed planet, beginning what would become one of the most successful missions in space exploration history. Cassini carried 12 scientific instruments and enough fuel to operate for years. It also carried the Huygens probe, a European-built lander designed to descend to the surface of Saturn's largest moon, Titan. Over the next 13 years, Cassini would revolutionize our understanding of Saturn, its rings, and its diverse family of moons. Cassini's close-up observations revealed that Saturn's rings are composed of water ice particles. The rings are divided into 7 main sections, labeled A through G, with the most prominent gap, the Cassini division, separating the A and B rings. These gaps are maintained by the gravitational influence of Saturn's moons, which shepherd the ring particles into distinct bands. One of Cassini's most important discoveries was determining how old the rings are. Scientists measured the rate at which dust and meteoritic debris accumulate in the rings. The surprising conclusion: Saturn's rings are relatively young in cosmic terms, perhaps only 100 to 200 million years old. This means Saturn existed without rings for most of its 4.5 billion year life. The rings likely formed when a moon or passing comet wandered too close to Saturn and was torn apart by tidal forces. As an object approaches a massive planet, the gravitational pull on the near side becomes much stronger than on the far side. If this tidal force exceeds the object's own gravity, holding it together, the object is ripped apart. The boundary where this happens is called the Roche limit. Saturn's rings sit within the Roche limit, which is why they can't coalesce into a moon. Saturn has 83 confirmed moons, but one dominates: Titan. This extraordinary world is larger than the planet Mercury and is the second largest moon in the solar system after Jupiter's Ganymede. But Titan's size isn't its most remarkable feature. It's the only moon in the solar system with a substantial atmosphere. Titan's atmosphere is thicker than Earth's, with surface pressure 1.5 times what we experience at sea level. The atmosphere extends hundreds of kilometers above the surface and is composed of 95% nitrogen, with most of the remainder being methane and traces of other hydrocarbons. This thick, hazy atmosphere completely obscures the surface at visible wavelengths, giving Titan a featureless orange appearance when viewed from space. For centuries, Titan was a mystery. Astronomers knew it had an atmosphere, discovered by Spanish astronomer Josep Comas Fim Solar in 1903 and confirmed by Gerard Kuiper in 1944. But what lay beneath that thick haze? Some scientists speculated there might be liquid hydrocarbon lakes or seas. Others thought the surface might be covered in a thick layer of organic sludge. Nobody knew for certain. That changed on January 14, 2005, when the Huygens probe separated from Cassini and began its descent through Titan's atmosphere. This was humanity's first attempt to land in the outer solar system and the first landing on any moon other than Earth's. For 2.5 hours, Huygens transmitted data as it descended by parachute through 150 kilometers of Titan's atmosphere. The probe's cameras captured hundreds of images, revealing a landscape that looked eerily familiar. There were river channels carved into highlands, drainage networks flowing toward lower elevations, and what appeared to be shorelines around dark patches that might be lakes. When Huygens touched down, it landed on what seemed to be a dried lakebed or floodplain. The surface was damp, but not liquid, described as having the consistency of wet sand or clay. Scattered around were rounded pebbles, smoothed by flowing liquid. The images stunned scientists. This looked like Earth, but the liquid wasn't water. At Titan's surface temperature of -179 degrees Celsius, water is frozen solid as rock. The liquid is methane and ethane, hydrocarbons that exist as gases on Earth, but as liquids in Titan's frigid environment. Titan has a complete methane cycle analogous to Earth's water cycle. Methane evaporates from lakes and seas, rises into the atmosphere, condenses into clouds, falls as rain, flows in rivers and streams, collects in lakes and seas, and evaporates again to continue the cycle. Cassini's radar instruments pierced Titan's hazy atmosphere to map the surface in detail. The images revealed vast hydrocarbon seas in the polar regions, particularly in the north. Kraken Mare, the largest, covers about 400,000 square kilometers, larger than Earth's Caspian Sea. There's also Ligeia Mare and Punga Mare, along with numerous smaller lakes. These bodies are filled with liquid methane and ethane, in some cases hundreds of meters deep. Cassini observed changes in these lakes over time, providing evidence of a seasonal cycle. Titan has seasons because, like Earth, its axis is tilted. Each season lasts about 7 Earth years. Cassini watched as liquid moved from the southern hemisphere to the northern hemisphere, evaporating from lakes in one region and condensing as rain in the other. Near Titan's equator, Cassini found vast dune fields covering millions of square kilometers. These dunes are made not of sand, but of tiny particles of organic material, complex hydrocarbons that have formed in the atmosphere and rained down over millions of years. The dunes are sculpted by winds in Titan's atmosphere and can stretch for hundreds of kilometers, rising over 100 meters high. Titan's landscape also includes mountains, possibly made of water ice that's as hard as rock at these temperatures. There are canyons carved by flowing methane, and there's evidence that beneath the surface there may be a liquid water ocean mixed with ammonia, kept liquid by tidal heating from Saturn's gravity. Titan's combination of liquid, organic chemistry, and energy sources makes it one of the most intriguing places to search for life in the solar system. The surface is rich in complex organic molecules, the building blocks of life as we know it. Liquid methane provides a solvent in which chemistry can occur, and there's energy from sunlight and cosmic rays to drive chemical reactions. Could life exist in Titan's methane lakes? It's hard to say. Life on Earth requires liquid water, but perhaps there could be life based on different chemistry, using liquid methane instead. Scientists have even speculated about what such life might look like, suggesting it could metabolize hydrogen and acetylene and breathe methane. If there's a liquid water ocean beneath Titan's surface, that might be an even better place for life. This subsurface ocean would be warmer, protected from the harsh surface environment, and if it's in contact with a rocky core, it could have the chemical ingredients necessary for life similar to that on Earth. While Titan captured imaginations, another of Saturn's moons provided perhaps Cassini's most stunning and scientifically significant discovery. Enceladus is a small moon, just 500 kilometers in diameter, about the width of Arizona. Before Cassini, it was thought to be a frozen, geologically dead world, interesting primarily for its high reflectivity. Enceladus reflects nearly 100% of sunlight that hits it, making it one of the brightest objects in the solar system. But in 2005, during a close flyby, Cassini detected something completely unexpected. Geysers of water vapor and ice particles were erupting from cracks near Enceladus's south pole, shooting hundreds of kilometers into space. These plumes were so powerful that some of the ejected material escapes Enceladus's gravity entirely, feeding Saturn's E-ring, a tenuous ring of tiny ice particles. The discovery was shocking. Enceladus is small, far from the Sun, and should be frozen solid. What could be powering these eruptions? Cassini flew through the plumes multiple times, using its instruments to analyze their composition directly. The results were even more astonishing than the discovery of the plumes themselves. The plumes contained water vapor, ice particles, salt, silica particles, and complex organic molecules including methane, propane, acetylene, and formaldehyde. The only explanation, beneath Enceladus's icy crust lies a global ocean of liquid water. How can a small moon have liquid water? The answer is tidal heating, the same process that makes Io the most volcanically active world in the solar system. As Enceladus orbits Saturn, the planet's immense gravity stretches and squeezes the moon. Enceladus's orbit is slightly elliptical, so the strength of Saturn's pull varies. This constant flexing creates friction inside Enceladus, generating heat. This tidal heating is strong enough to melt ice, creating a global ocean beneath the icy crust. The ocean is estimated to be about 10 kilometers deep, sitting beneath an ice shell roughly 20 to 25 kilometers thick. At the South Pole, the ice is thinner, and cracks allow ocean water to reach the surface and erupt into space. The presence of silica particles in the plumes is particularly significant. On Earth, silica forms when water at temperatures above 90 degrees Celsius interacts with rock. The only way silica could be in Enceladus's plumes is if the ocean water is in direct contact with a rocky seafloor and is being heated to high temperatures. This means Enceladus has hydrothermal vents, underwater hot springs similar to those found at the bottom of Earth's oceans. On Earth, these hydrothermal vents are oases of life in the deep ocean, supporting entire ecosystems without any sunlight. They provide chemical energy that microbes can harness, forming the base of a food web. The discovery that Enceladus has liquid water, organic molecules, chemical energy, and hydrothermal activity makes it one of the most promising places in the solar system to search for life. It has all the ingredients: liquid water as a solvent, organic molecules as building blocks, chemical energy to power metabolism, and minerals from the rocky core to provide nutrients. Scientists now consider Enceladus a high-priority target for future missions. A spacecraft could fly through the plumes and collect samples without even landing, analyzing them for signs of life. Some scientists have proposed sending a probe that would melt through the ice to directly explore the ocean beneath. The fact that Enceladus is actively venting its ocean into space is remarkable. It's as if this moon is offering us samples of its interior for free. We don't need to drill through kilometers of ice. We just need to fly through the plumes and collect what Enceladus is giving us. The discoveries at Enceladus, Europa, Titan, and possibly other moons have fundamentally changed our understanding of where life might exist. We used to think life required a planet in the habitable zone, the narrow band around a star where temperatures allow liquid water on the surface. Earth sits in the Sun's habitable zone, but Mars is at its outer edge and Venus at its inner edge. But we now know habitability extends far beyond the traditional habitable zone. Tidal heating can maintain liquid oceans billions of kilometers from the Sun, in places we once dismissed as frozen and dead. The habitable zone isn't just a thin band around stars. It extends throughout solar systems wherever there's enough energy to maintain liquid water. This has profound implications for the search for life beyond Earth. If small moons like Enceladus can harbour oceans and potentially life, then similar environments could exist throughout the galaxy. Every gas giant with moons could potentially have habitable worlds. And gas giants are common. We've discovered thousands orbiting other stars. The universe may be filled with ocean worlds hidden beneath icy shells, warmed not by starlight, but by the gravitational embrace of giant planets. Life may be common in places we never thought to look. As we reflect on Jupiter and Saturn's influence, we see that these giants have shaped the solar system in countless ways. Their migrations redistributed matter, creating the solar system architecture we see today. Their gravity continues to perturb asteroids and comets, occasionally sending them toward Earth. But most remarkably, their gravity has created some of the most dynamic and potentially habitable environments in the solar system through tidal heating. Io, Europa, Ganymede, Callisto, Enceladus, and potentially Titan all owe their geological activity to tidal heating from their parent planets. Without Jupiter and Saturn, these moons would be frozen, dead worlds. Instead, they're active, complex, and in some cases potentially inhabited. In a very real sense, we are all children of giants. Earth owes its water and perhaps the seeds of life to material delivered during Jupiter's migration. Our existence depends on Jupiter's protective influence shielding us from excessive bombardment, and the other potentially habitable worlds in our solar system owe their habitability to tidal heating from Jupiter and Saturn. The next chapter in solar system exploration will focus on these ocean worlds. NASA's Europa Clipper mission, scheduled to launch in October 2024, will conduct detailed reconnaissance of Jupiter's moon Europa. The spacecraft will make dozens of close flybys, using radar to probe the ice shell's thickness and study the ocean beneath. It will analyze plumes of water vapor that occasionally erupt from Europa's surface, searching for organic molecules and other signs of habitability. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023, will study Ganymede, Callisto, and Europa. It will map their surfaces, probe their interiors, and search for subsurface oceans. NASA's Dragonfly mission, set to launch in 2027, will send a nuclear-powered helicopter to Titan. This car-sized rotorcraft will fly from site to site across Titan's surface, covering hundreds of kilometers. It will study Titan's organic chemistry, investigate the methane cycle, and search for chemical signatures of past or present life. Looking further ahead, scientists are planning missions to Enceladus. Proposals include spacecraft that would fly through the plumes and collect samples, or even landers that could analyze the ice and perhaps drill down toward the ocean. These missions represent humanity's next great steps in exploring the solar system and searching for life beyond Earth. The answers to some of our most profound questions may lie not on distant exoplanets, but right here in our cosmic backyard, on moons we once thought barren and lifeless. From Pluto's beating heart to Enceladus's erupting geysers, from Ceres's sparkling salt deposits to Titan's methane seas, from Europa's fractured ice to Io's volcanic fury, the worlds of our solar system have revealed themselves to be far more dynamic, complex, and wondrous than we imagined. The solar system's story is one of chaos and order, destruction and creation. It's a story where Jupiter and Saturn played central roles, their migrations sculpting the architecture of worlds. They scattered asteroids, stunted Mars, cleared the inner system, and delivered the ingredients for life to Earth. Their gravity continues to shape the system, occasionally threatening Earth with impacts, but mostly shielding us from catastrophe. Most remarkably, these giants have created habitable environments through tidal heating. Their gravitational embrace keeps oceans liquid on moons billions of kilometers from the Sun. Life, if it exists on these worlds, owes its existence to the pull of giant planets. We stand at a threshold in human history. For the first time, we have the technology to explore these ocean worlds and search for life beyond Earth. The discoveries of the past decades, subsurface oceans, organic chemistry, hydrothermal vents, and erupting geysers, have shown us where to look. The question of whether we're alone in the universe may soon be answered not by detecting radio signals from distant civilizations, but by visiting the moons in our own solar system. The answer may lie beneath the ice of Europa or Enceladus, in the methane lakes of Titan, or in places we haven't yet explored. Every mission teaches us that the universe is stranger and more wonderful than we imagined. Every world we visit reveals new mysteries, and every discovery reminds us that we're part of something vast and ancient, a cosmic story that began 4.6 billion years ago and continues to unfold among the stars. The King of Gods has shaped our destiny, sculpted our world, and created the conditions that allowed life to flourish on Earth. As we venture outward to explore the realms Jupiter commands, we're discovering that this giant planet's influence extends not just across space, but across the possibilities of life itself. The solar system's story is far from finished. In many ways, we're only just beginning to read it. And as we continue exploring, we carry with us the knowledge that we live in a system shaped by giants, where the dance of planets billions of years ago determined which worlds would become oases of life and which would remain frozen in time, fossils of an earlier age waiting for us to unlock their secrets.